Consider these two birds. We as humans can easily infer the similarities across them. For example, if we highlight this pixel on the bird on the left, we understand that the corresponding pixel on the bird on the right is here. And we can similarly infer associations for all the pixels shown across these two objects. That is, we can infer the corresponding pixel on the other object or realize when the corresponding pixel is not visible. This task of inferring inter-object correspondence is a fundamental one across various vision, robotics, and graphics applications. But a key question is, how can we acquire these correspondences? How can we learn to infer these correspondences between these two images? There have been several attempts in the past for this task of learning dense correspondences. In particular, work by Guler et al. Used dense annotation as a form of supervision to learn this task. However, collecting such dense annotation is tedious and can only be done for specific categories of interest and is hard to scale to generic classes. To reduce this form of supervision, work from Zhu et al. Instead relied on synthetic data and pose annotation on real images and learned dense correspondence using a cycle consistency loss. However, this requirement of lots of synthetic data and pose annotation on real images is still tedious, and there have been approaches which attempt to even relax this form of supervision. Work from Kanazawa et al. And Thewlis et al. Generates data in a self-supervised manner by randomly warping real images and using these randomly warped pairs as supervisory signal to learn dense correspondence. However, these random warps are limited to be in-plane transformations and cannot generate significant viewpoint transforms, and further, these approaches ignore the geometry of the underlying task. We present an approach that similarly does not leverage keypoint annotations or pose annotations to learn dense correspondence, but uses the geometry of the task to learn this. In particular, instead of learning the 2D to 2D correspondence between two images directly, we instead learn 2D to 3D correspondence, and note that this 2D to 3D correspondence should be consistent with a 3D to 2D reprojection, and use this geometric consistency as supervisory signal to learn this 2D to 3D correspondence. Formally, we tackle the task of canonical surface mapping, where our goal is to learn mapping from image pixels to a template 3D shape. That is, given any pixel, we aim to infer the corresponding 3D point on the template shape. We do so by learning a CNN that takes as input this image and outputs a per pixel canonical surface map that indicates the corresponding point for each pixel on the template shape. As an illustration, we show the coloring of the template shape and note that similar colors imply that we have inferred correspondence between the 2D image and the template 3D shape. To parameterize the space of predictions, we note that the surface of any 3D mesh is actually a 2D manifold living in 3D, and we can construct a bijective mapping between a 2D square and this 3D surface. This is analogous to parameterizing a sphere by a latitude and longitude corresponding to each point. We call this 2D space a UV space, and note that the task of our CNN is reduced to making a per pixel UV prediction that implicitly corresponds to predicting a 3D point at each pixel. We train the CSM prediction CNN by enforcing geometric consistency. Given a camera pi corresponding to the image, we enforce that the per pixel CSM predictions should be consistent with the reprojection of the template shape under the camera pi. We call the loss enforcing this a geometric cycle consistency loss and look into it in more detail now. Given this image for which we have a corresponding CSM prediction, we consider a particular pixel for which we have implicitly predicted a 3D point by the mapping phi. We enforce that this 3D point, when reprojected back onto the image under camera pi, should project back to the original location and use the inconsistency between the original and the reprojected location of this point as a loss function. We add an additional term enforcing some visibility constraints that ensures that the 3D point projects to the visible surface as opposed to the occluded surface. We explain this in more detail in the paper. Using this geometric consistency loss, we can train this per pixel CSM prediction system, but our description so far assumed a known camera corresponding to this image. We note that we can simply learn to also predict this camera, and therefore train an additional CNN that, given the image, also predicts this camera pi and enforce the cycle consistency between the predicted CSM and the predicted camera. Unfortunately, the framework described so far, where the camera pi and CSM are jointly learned to be consistent with each other, can lead to some degenerate solutions, and we therefore need to add an additional reprojection loss to prevent such solutions. The framework allows us to learn this 2D to 3D canonical surface mapping prediction by enforcing geometric consistency, and allows us to bypass the requirement of key point or pose annotations, and therefore we can scale to generic categories where such annotations are difficult to acquire. However, our framework does have some limitations in that it cannot handle large shape deformations or articulations because we aim to explain all the data using reprojections of a fixed template shape. We show some results here where again similar colors highlight inferred correspondence. For the bird and car categories, we used Cub and Pascal datasets respectively, where ground truth segmentations were available. For the other classes, we simply used ImageNet images with segmentations inferred from an off-the-shelf detection system. Further, for the zebra category, we simply used a horse template shape. This shows that our method is robust to imperfections in both template shape as well as the foreground mask annotations. Our predictions can allow us to explicitly recover the 2D correspondence between images. That is, given a pixel PS on a source image, say the one on the left, we can infer the corresponding pixel in a target image. To do so, we note that the predicted CSMs implicitly map this pixel PS to a 3D point on the template shape, and we can find the corresponding point PT by simply searching for the pixel that maps closest onto this template shape. This allows us to transfer key points from source images to target images. As an example, we show results here for the bird category, where given source images on the top, we transfer the annotated key points to target images shown at the bottom. We also show similar results for cars, and note that we can quite accurately transfer key points despite relatively large viewpoint changes. We also empirically validate our approach by measuring its ability to transfer these key points accurately, and compare to previous approaches that use similar or more amount of supervision, and observe that our approach that leverages the geometry of the task can outperform these previous methods. We also show some results on videos in the wild, where we simply apply our learned system on a per frame basis. Note that our system was trained only using unoccluded and untruncated images, so we observe some error modes corresponding to these.
Or carrots or apples?
Making him hungry.
Thank you for your attention. Please see the project webpage for code and more details.